Clerk Maxwell Telescope Group, and currently an associate professor at Queen's University. And her professional interests are galactic structure and interstellar medium. And she'll be speaking tonight on pinwheels, ellipsoids, cannibals, and shreds, and we'll look at galactic structure. So join me in welcoming Dr. Irwin.
Anyway, thanks very much for the invitation to come up to Ottawa. It's nice to be here. My brother lives in Ottawa, and I'm staying with him and his family over the weekend, so it's a great opportunity to come up and to meet you here and to spend the weekend with them as well. I understand you burnt down a golf club to do this. I'm not so used to giving after-dinner talks. I'm used to being in a lecture theater with 200 students and forcing them to pay attention. So it's a little different. And I was talking to a colleague of mine earlier this week, and also an astrophysicist, a theorist, walking along and saying, well, you know, I have to give this after-dinner talk. I should really have a wise saying or something, you know. And he quickly rising to the challenge, he said, how about we are spiders sitting on the nodes of our cosmic web, hoping to catch every photon that comes our way. And I said, thanks anyway. So I'm afraid that's about the best we can do tonight for wise sayings, but I hope that I'll be able to mention a few things that are of interest to you at some point. Okay, so today I thought I would talk to you about a subject which has become more interesting to me recently, and for reasons that will become, maybe you'll remember by the time we get to the end of the talk. I guess basically because of some data mining that I'd like to do with a student of mine. But I thought it was time maybe to look at galaxies and to consider what we know, not so much what we know about them, but what we know about how they look, and how we need to make some changes, I think, in the way we look at them in the future. So you see a few pictures of galaxies that I've grabbed here, including our own, which is down at the bottom left, the infrared. I'd like to start by reminding everybody that we haven't known that galaxies exist as galaxies for very long. There was quite a debate around 1920 as to whether the spiral nebulae, as they were referred to, were actually part of our own Milky Way system. And in fact, this picture is sort of the way the system was seen by Harlow Shapley, who in fact displaced the sun from the center of our galaxy outward. And he thought that these spiral nebulae were actually part of our own Milky Way. And a few years later, after this debate, Edwin Hubble managed to find what we know as a Cepheid variable star in M31. And you can see his, point on here, his little remark here on the side saying variable with an exclamation mark. And the Cepheids allowed him to find a distance to M31, which is in fact at least a factor of 2 too low. But it was still large enough that it became very clear that these were separate systems and not part of our own Milky Way. So they were referred to as island universes, which we don't see them so much that way now, but certainly they appear that way in the sky. And Edwin Hubble then worked on a classification scheme for these spiral nebulae, these galaxies. Oops, I keep hitting the wrong one. Okay, that's all right. Okay, so he spent a while developing a classification scheme, and I guess the question comes to mind of why even bother classifying. And obviously this is something that many, many fields do, especially in the early stages when they're trying to make a lot of sense out of diversity. What you're really doing is trying to search for some kind of order and ultimately to get at origins in the midst of seeing many different kinds of structures. In fact, I can remember when I was in graduate school at the University of Toronto, I took a course in galaxies, and the professor came in with a small plastic bag filled with black grainy material, and he put it on the desk and he said, okay, I want you all to classify everything in here make up a classification scheme for it, and write it up APJ style, meaning in the style of the Astrophysical Journal. And I spent many hours with a microscope going through all the little grains and making up a classification scheme and finding that, in fact, about 8 or 9 seemed to work. And I could see rods, and I could see spherical objects, and I could see a variety of sizes, and then I could see a few little shells. And I developed my water erosion hypothesis, and I wrote it all up in paper and handed it in. And it was kind of fun, and in fact, it's probably the only exercise I strongly remember from that time period, as many of your teachers, those kinds of activities are the ones that your students tend to remember. But it was interesting to do it, and it certainly gave us a feel for the kinds of challenges that face classifiers as they do their work. So this is the scheme that Hubble came up with. It's a tuning fork diagram, which I'm sure most people have seen here. And you can see that on the left-hand side, we have these so-called elliptical nebulae. And on the right hand, we have the spirals. And the spirals split into 2 groups, whether they're barred or whether they're unbarred. And Hubble himself coined the terms early and late type galaxies, saying in a footnote that he did not intend this to represent any kind of evolutionary pattern. The terms early and late type galaxies are still used, and they certainly do not refer to any evolutionary pattern, although the thought was that perhaps at one time they might. If anything, it goes the other way. Okay, so in a little more detail, here's his tuning fork diagram, and he classified according to 3 criteria. The first one was the bulge-to-disk ratio, meaning how big was the bulge in comparison to the disk. The second one was the degree of openness of the spiral arms, and the third one was the degree of resolution of spiral arms in 2 knots. Now, as you go to the right, you see more open arms and you see more knotty kinds of arms, and you see smaller bulges in comparison to the disks. And for the most part, that seemed to work not too badly. But because there were 3 criteria, there were always galaxies that didn't quite fit, meaning that they might have small bulges but tightly wound arms, for example. And so it was seen really from the beginning that this was a sort of guideline classification scheme, but certainly there were galaxies that didn't quite fit into the scheme the way the way most of them did. Also, the resolution depended upon the resolution of the telescope. And then what did you do with galaxies like this? DDO, as you may know, is a David Dunham Observatory number. And often these are dwarf, most of these are dwarf systems. But certainly it became clear also that there were a number of galaxies that really didn't fit into that typical tuning fork, including M82. And so another bin was needed, and actually we found this for our black sand in our little experiment, that there were always a few that didn't quite fit and got into their own bin, just called irregular. Some years later, de Vaucouleurs, the French astronomer working in Texas, developed a somewhat more complex scheme. And the idea was to try to fit in more of the diversity of features that that were apparent in the galaxies. And these are sketches on the right-hand side here. On the, I can't quite make out these letters very well, but A would be sort of a typical spiral, B would be a barred spiral, so you can see the difference from this side to that side. And then on the right, there'd be an R classification for a ring, and on the left, there'd be an S classification for a spiral. And so this was represented as a classification volume with in between, as you can see, going around like that. And this scheme is more or less the one which we use today. If you go to the NASA Extragalactic Database on the web, this is the kind of classification you'll see beside the galaxies. Okay, so now let's ask, well, we have a scheme. How well do the experts agree on their classification? And in a proceedings of a workshop held just a couple of years ago, this is the kind of comment that was mentioned, that for Galaxy NGC 3081, Sandage would classify it as capital SEA with a spiral. De Vaucouleurs would call it whatever you see on the right there. And Utah would call it the longer one on the right. That I couldn't do. Actually, it's R subscript 1, R subscript 2 primed. And to be fair, they have their own systems, and presumably they can classify within their own systems. But it's also true that even if you get experts trying to classify via the same system, they will often disagree. And so the solution, of course, is to get rid of the experts. So saying that tongue-in-cheek, of course, but this is being taken quite seriously. The idea is, of course, to agree on some kind of a system, and then to do a classification in a more automated fashion. And of course, we certainly need to do this as more and more data come in. It's just not possible anymore for the experts to sit down plate by plate and do their classification. And so the idea is to scan things automatically and to classify. You mentioned neural networks there. The problem with neural networks, as has been applied to galaxies, is that you have to teach them first. You have to actually teach them what kind of classification you want, and then throw in all the galaxies that you don't know the classification for and hope that they can do it right. So, is there general agreement about a classification scheme right now? And the answer is yes, but only if you kind of ignore all those little details. And when I say little details, I mean those things that are quite obvious to us. Spiral structure, bars, rings, resonances, and so on. And it may be fair to do that because spiral structure, for example, is really a perturbation on underlying mass distribution. So the fact that there might be a spiral there or not may not be of primary importance in terms of the galaxy if you're asking questions about its origin. But if you look at those three galaxies, for example, the one on the right, this is not a ring, which is just some resonance ring on the right-hand side. This is actually a ring created from two galaxies colliding with each other. And I think in that case, you certainly cannot ignore the structure. Is there general agreement about a useful classification system, period? And the answer is no. That's it. Okay, scientists like numbers. And so what's generally done, or has been done, is to take some scheme that you're happy with, at least for the most part, like de Vaucouleurs, and then turn those classifications into numbers. And so that's been done. Actually, it's more in terms of the Hubble type than the de Vaucouleurs type. But the idea is to assign, say, an early type galaxy as just calling it a 0, and heading off down the tuning fork diagram and calling a late type galaxy a 10. And although this may be treading into difficult waters, at least you can say, okay, I've got some number scheme. Whether this scheme, the Hubble scheme, is meaningful or not, we don't know. But then I can at least try to take those numbers and see if they correlate with any physical properties. Now, this has been done quite a lot. It's been attempted quite a lot. And let's consider the ellipticals first. The fact is that the elliptical galaxy morphology doesn't correlate with any physical property. It doesn't correlate with mass, it doesn't correlate with luminosity, velocity dispersion, color, surface brightness, or anything. The shape of the elliptical galaxy, as you can imagine, if there's some ellipticity to it, of course we're just seeing it projected on the sky. And just getting back at the distribution, the intrinsic distribution from a projection is in itself non-trivial. But it's well known that the elliptical galaxies do not correlate with any physical property. The solution has been to ignore the Hubble type altogether and to examine a sort of physical parameter space. And this has actually been done with some success for elliptical galaxies, partly because they are simple systems, relatively speaking. They are what we call virialized and relaxed systems. And so they have certain parameters which do correlate with certain other parameters. Now for spirals, they're not quite as simple. And it turns out that spiral galaxy morphology doesn't correlate strongly, or there isn't at least convincing evidence that the T-type correlates with any physical property except color. And color relates to a star formation rate. The bluer the galaxy is, the more active star formation is going on in it. Solution, well, hanging on to the Hubble type at least we do know that there's a bulge to disk ratio variation across the Hubble types. That is, in fact, a definition. And that should be some structural parameters, so people don't really like to throw it out. And besides that, there just isn't anything else at the present time. Okay, there's another problem, and I'd like to illustrate it with this galaxy, NGC 253, and I've just listed its type at the top. This is a typical optical picture, one that you see here on the left, and this is the infrared picture on the right. 2 microns. Now you see very vividly one of the problems with morphological classification. There's no way that you're getting the same result if you look at the 2 different wavebands. It's very clearly a barred spiral on the right. On the left, there's actually a hint of a bar, but certainly not as easily seen as the right. Now, hot stars give the most light and cool stars give the most mass. So in fact, I would argue anyway, that if we're going to do any classification at all, we should certainly do it in the infrared and not optically. Because if there are hot blue stars, they will, actually the luminosity goes as the mass to some strong power. It could be mass to the, say, the 4th power. And that means that even if you have very few hot stars, they will make a very strong perturbation on the light that you see. Whereas they're not really making that stronger perturbation on the mass, because most of the mass consists of the low mass stars, which are spread out somewhat differently in the galaxy. Here's another example. I'm going a little bit farther afield now. Rather than just tuning to infrared band, let's look at something completely different. Let's look at the neutral hydrogen content in the Large Magellanic Cloud. And that's what it looks like. This is not an irregular galaxy. The underlying gas distribution is actually quite circularly symmetric. But in the sky, we're seeing those hot stars, and we're seeing a very strong weighting towards where the hot stars happen to be. I threw this one in simply because it's data that I got. But anyway, it's meant to show you the H1 distribution around a galaxy, just to show you how different it can be. The optical galaxy is in here. This is NGC 3556. And it's an edge-on galaxy, and the H1 distribution is enormous in comparison. There's actually a long tail here as well. And this is just one particular velocity on the bottom, where you can see a very large shell of gas. This is a hole in the middle, coming out of the side of this galaxy. Extremely different picture when you look at the gas instead of the stars. So then you might ask, well, what would galaxy classification look like if we had X-ray eyes, for example? Of course, we have to get above the atmosphere to see anything. But I think that if you started from scratch and your eyes were not tuned to optical wavelengths but X-ray instead, you would have an entirely different classification scheme for galaxies, mainly because you're not just seeing the same thing, brighter or dimmer, you're seeing entirely different things. This is the same galaxy I just showed you, the barred and the one that didn't look so barred. And in the X-ray, you can see enormous X-ray plumes. This is very hot gas, 10 to the 6 Kelvin or so, coming from the nucleus of this galaxy. So what would a galaxy classification look like if you had X-ray eyes or radio? Here we have Centaurus A in the optical, and radio jets coming out from the nucleus. All right, so we can see these things, and you might say, well, if we just observed at enough wavelengths, maybe we could fully characterize the galaxies, and that could be. That's something that you work towards. But we are now in a time of discovery of galaxies. We continually discover new galaxies by just going deeper, etc. And the question question is, the question might be, are we just finding more of the same, or are we finding new kinds of things altogether? And the first point I'd like to make in this regard relates to the RASC galaxies. Now, this was a satellite that went up in the 1980s and observed many galaxies in the infrared, 12, 25, 60, and 100 microns. This is M31 in the, I forget which wavebands that is, the IRIS wavebands. And what IRIS managed to uncover was many galaxies that were extremely strong infrared emitters. And what that meant, because it was the long wavelength infrared, not the short wavelength like I showed you before for NGC 253, what you're looking at in the long wavebands is dust. You're looking at the emission from dust. And that means that because there was such strong dust emission, that galaxies in the distant universe were enshrouded in this dust and were emitting strongly. Well, why would that be? It's because that the hot stars within that galaxy were having their light absorbed by the dust, which means that you would not see them very strongly optically, but you do see them strongly in the infrared. And so it's not as if IRS picked up all kinds of new kinds of galaxies, but what it did was showed how many galaxies were dust enshrouded that you couldn't see so well optically, and many of these happen to be interacting galaxies. Nowadays, more modern, is the SCUBA detector on the JCT, James Clerk Maxwell Telescope, of which Canada is a partner. You can see it here. It's in Hawaii, and I'm showing you a very noisy image, but there's a whole class now which has really become obvious to people within the last, I'd say, 3-4 years, that there's a class of sources, and you can just barely make out the source in this particular frame, which is emitting at 850 microns, which means that this is cold dust emission, cool dust emission. And when you look optically, you don't see anything. In other words, these distant galaxies, believed to be distant galaxies, are so, there are many, many of them. We don't have census yet. But they are so enshrouded in dust that we don't see them at all optically. They were completely invisible. Again, this may not be a new kind of galaxy, but it certainly changes our view of what could be out there. All right, let's take a look at M101. It has a magnitude of B of 8.31. And now let's take a look at Malin 1. This is a low surface brightness galaxy. You can see the magnitude is 16.2 for this one. Now compare the masses of the two systems. The mass of M101 is around 4 10 to the 11 solar masses, and Malin 1 is a couple 10 to the 12 solar masses. In fact, the neutral hydrogen gas in this galaxy alone is as much as all of the mass in this galaxy. And this study of low surface brightness galaxies really opened up in the 1980s, and much work has been done now to show basically what everybody in this room knows, that it's just difficult to get below certain surface brightnesses. And there's now a specific classification of these galaxies such that their central surface brightness cannot be, or is below some limited magnitude per square second. So these are also the new discoveries, although you could argue that maybe you are seeing similar kinds of things that you're seeing now. The difference seems to be, however, that in galaxies like this, the star formation rate has just declined for some reason. It's thought that perhaps the surface density of gas in the galaxy, although there may be a lot of it, at any given position, it may not be sufficient to start a star formation process. And so what we've been seeing for years and years are, and thinking that they were normal, are high surface brightness galaxies where the star formation has actually proceeded at a more rapid pace. The other problem is that when you really look in the deep universe, the Hubble classification scheme breaks down completely at redshifts greater than about 1. So when you look in the Hubble deep field, for example, you'll see some galaxies which look sort of like what you've seen before. But if you do a more detailed analysis, what you tend to see are more like shreds of galaxies. or bits and pieces of galaxies. And this actually factors into current views as to how galaxies are formed. That when you look far away in the deep universe, you're also looking back in time. And this was a time when galaxies were forming, and shreds or bits and pieces were coming together to form larger systems that we see now. So what we need to do then, not only do we have a classification scheme that doesn't seem to work great for galaxies nearby, it certainly doesn't work at all if you go deep. And that means that you have an evolution of morphology. So we need to understand morphology in the context of galaxy formation and evolution, and we need to do it within some cosmology. Well, do we have a good paradigm for galaxy formation? And yes, and this is our spider web, by the way. I think we're sitting on a node in there somewhere. Yes, we do actually have a reasonably good paradigm for galaxy formation. It doesn't work perfectly, but it's something to work within to try and get at what's really going on, except for one tiny little detail. Oops. And that is that 98% of the mass of the universe is not accounted for. Now, this is a bit of a problem. What we see is only a tiny fraction of what's actually there. So, what does this mean? Obviously, most of the universe, most of the matter in the universe is dark and has not yet been detected. In fact, there's a growing body of scientists who are leaning towards gravity actually having to be modified than to say that there's all this missing mass, but that's another story in itself. At any rate, the current view is that we are missing most of the mass of the universe. We don't know what it is. In fact, I was mentioning this in a class last week and realizing for myself that we still are looking for objects that could be dark matter over a range of 72 orders of magnitude. From an axion, which is 10 to the minus 6 electron volts, to a few hundred solar mass black holes. It's a huge amount. We really do not know what this stuff is, although we have some ideas about whether it's baryonic or non-baryonic. So around our Milky Way, we have maybe a few 10 to the 11 solar masses in the Milky Way in visible material. And when I say visible now, I mean everything that's luminous at any wavelength. Okay? So if you add all that up, you get maybe a few 10 to the 11 solar masses for the Milky Way. And the dark halo around it has about 10 to the 12 solar masses, it's thought. So here's Kobe's infrared view of the Milky Way. And here's the dark matter halo. We don't know. Most people think it's spherical or slightly flattened, but we don't know if we figure that out. Now, this was supposed to be a simulation, but I'm new to PowerPoint. And it worked at Queen's, honest. But I tried it here, and unfortunately I didn't get to work. It was meant to be a simulation of what's called cold dark matter, which is, there are problems with the cold dark matter scenario, but let's just say that it's a scenario which has the least problems in terms of predicting how galaxies are formed. And you basically let cold matter decouple from the light matter as the universe expands, and then gravity does its work and pulls back certain pockets and so on, and makes the galaxies. Of course, I can say anything, right, because you can't see anything there. I'm just making it up. Anyway, so there was supposed to be a simulation. You just have to take my word for it. Okay, come on. All right. So now that we have all these so-called problems, is there any hope at all of uncovering so-called order and origins from galaxy morphology? And I think the answer is yes, or yes, if. Okay. First of all, you need to find fossils of the galaxy formation process. In other words, entropy is working against you, right? We all know that you can take two temperatures in a box and let them join together, and they'll both come down to some median temperature. But the first two temperatures could be you know, very high and very low, or just a bit high and a bit low, right? And they'll still come to the same temperature. And this is the problem that you're always fighting against with understanding where the origins are with galaxy formation and where we are now, because much of the information will simply be wiped out in the process. And so you need to focus on at least, if not more, on those things which might remain fossilized in a sense from the time of the origin of the galaxy. And we do have such fossils in our own Milky Way. For example, the globular clusters. Globular clusters are extremely old. They're as old almost as the universe. And they are some of the first objects which are formed after these shreds started coming together. And also the metallicity of some of these objects is very important, because the metallicity tells you about the star formation history of any given region. On the right-hand side, I'm showing you a picture of our Milky Way in the optical, but superimposed is sort of a sketch of Sagittarius A dwarf, which is a galaxy currently falling into the Milky Way. And it's thought that the Milky Way and other galaxies built up from such infall, and that it still goes on today. So in fact, galaxies are still forming, and we're still seeing the effects of smaller dwarfs being accreted into our own Milky Way. So that's one thing that we can do, is to look at those kinds of signatures. The other thing I think we have to do is to discard our optical bias, which I've more or less already mentioned. I'm just showing you here a picture of part of our Milky Way in neutral hydrogen. This is data taken from the Canadian Galactic Plane Survey at Dominion Radio Astrophysical Observatory in Penticton, BC, which is doing a marvelous job of mapping out the neutral hydrogen distribution in our Milky Way. And you see a section out here. I think you'll agree it doesn't look anything like the optical. And new features are showing up in these, such as have never been seen before. And I think the third thing we need to do is completely discard our old schemes and to look systematically for physical correlations and to look at them with fresh eyes. There's been reluctance to walk away from Hubble, because at least, I don't mean the person, I mean the scheme, because at least when you say SC, people kind of have an idea what that looks like. And that's a good thing, right? We want to have some feel for what a galaxy looks like. But I think in terms of, if we really want to get at the components, the important points, the underlying mass distributions, what's actually driving all of this, then I think we have to start again. And now is the time to do it. And the reason is because if you go up to the web one day and do a search and put in something like astronomical surveys, and you'll come up with something like 100 that are going on now. Of course, they're different wavebands and they're different places and so on and so forth. But this is really the age of data acquisition, such as it has never been before. Now, some might argue that this is not a good thing, because all we're doing is collecting data. We really want to understand it. But I would say, well, at least you have to get it first, and then we'll work on it, right? So this is just a picture of these are all galaxies in the APM, it's called the APM survey, such as it's been carried out thus far, but there are many, many others. There's the Sloan survey, there's surveys at other wavebands. There's much that's going on now in this area, and what we need to do is to gather the data and start mining it, and to mine it completely, just completely afresh. In fact, I predict there's always been this at least two kinds of astronomers, professional astronomers. You know, there'd be the theorist and there'd be the observer. And I predict that in the future, you'll see the theorist, the observer, and the data miner. That seems to be the direction that we're going. And with that, I think I'll stop. Thank you.
I have two questions. The first one is, I'm very disappointed the fact that even with the latest books and information that I have, there doesn't seem to be very much on the galaxy, especially the elliptical galaxies. The their motions within the stars, the orbits, the rotation, all the dynamics. They know all kinds of things about the spirals, you know, the arms, and Frank Hsu and his theory of the arm movement and things like that, but there doesn't seem to be anything. Could you clarify for me, what did they know? What's the latest in dynamics of the ellipticals?
Well, the ellipticals, I mean, there has been quite a, actually, there's what you call a fundamental plane. There's been a lot of work done on ellipticals to try and piece together all these physical properties, like just forgetting about the Hubble classification. These are highly virialized systems, which means that you can practically describe the motions of the stars within them by a Maxwellian distribution. You know, so they're simple in that sense. There doesn't seem to be much rotation. In other words, the stars are individually going around in their own orbits, and the shape of the elliptical is given by the fact that the stars go around in a certain way. It's not as if you're getting a flattening from rotation or anything like that.
So there's little rotation of the galaxy itself.
That's right, unless you go to the dwarf ellipticals, and they are actually different. There does seem to be some rotation, I believe, for the dwarfs. If you want, I could try and find, I have some information about what's called the Galaxy Manifold, and it's a plot in 3 dimensions that shows how the luminosity relates to the velocity dispersion of an elliptical, and how that relates to I think it is the surface brightness, and the luminosity correlates with the mass and various other things. So instead of saying it's a type whatever, you say, well, it falls on this position in the Galaxy Manifold. And there is some sense out of that, but apparently it breaks down at the low magnitude, at the dwarf stage.
Isn't
the dwarfs
this
are
what
something
Tully
else.
did? Tully did this kind of work, didn't he, in Hawaii?
Brent Tully?
Yeah.
Well, there's
Sort of
There's a Tully-Fisher
brightness mass correlation.
Okay, now you're talking about the spirals. That's the Tully-Fisher relation.
Oh yeah.
And
that does not apply to the ellipticals?
No, but there's a similar relation called the Faber-Jackson relation for ellipticals, but it's something similar. Now basically, the Tully-Fisher relation, what it says is that the brighter the galaxy is optically, the faster it rotates. And the rotation depends upon the mass, right? So the more massive it is, the faster it will rotate. And the brightness is also correlates with that, the intrinsic luminosity. So then what you can do is look at the actual brightness you measure at the Earth and get a distance. So it's used to measure distances, the Tully-Fisher relation. But the fundamental principle is very puzzling, because the rotation depends upon the mass, but all mass, light and dark. But it correlates perfectly with the luminous mass, which is what you see. So that is a very, very puzzling, because most of the mass should be dark, and it shouldn't be what we call baryonic. So this is just an open question. We don't know the answer to that, why that correlates so well. It does. So anyway, the elliptical galaxies have a similar correlation, but it's a separate correlation, but it's similar in the brightness and the dispersion of the velocities.
Now, Dr. Irwin, were you saying that we probably should be classifying galaxies based on their infrared face that they put forward?
I'm saying if you're going to do it at all, and if you're going to put weight on that and say, I want to classify by morphology, then you should at least do infrared, yes, because you're looking at most of the mass then. Whereas in the optical, you're just looking at a few bright stars, basically, in comparison to the number of faint stars.
Right, but isn't there a danger, though, that maybe the barred aspect of a spiral galaxy isn't its most, in a sense, isn't its most important feature?
Yes.
Could we be sidetracking ourselves on that and not looking for the other?
Yeah. Yeah, my own opinion is that you shouldn't bother at all. But if you're going to do it, you should do it in the infrared. Right. The barred aspect, that illustration was just kind of nice to show you how different things can look in the different bands. But I agree that the barred, whether the galaxy has a ring, a bar, or spiral structure, these do appear to be perturbations, right? I mean, the spiral structures may be beautiful, but what you're seeing is, you know, 1/10 of a perturbation in mass around it. Is that really what's important? And in fact, often what can drive spiral structure is an interacting galaxy. So that's not going to get you at any real origin. That's going to tell you something about the interaction. want to get at some origin. So spirals are nice, but they're not necessarily telling you about the galaxy.
Are we getting close to finding out where quasars fit into all this?
Oh boy. Well, quasars, yes, I think we're farther ahead. Quasars are quasi-stellar objects. They're active galactic nuclei. Okay? And it used to be that all you would see is a very bright object, like a point source, quasi-stellar. But now it is true that you can see the galaxies around them. So it's pretty clear that these are active galactic nuclei within a galaxy. As far as I can recall, it was more likely that you'd get a quasar within a galaxy that was interacting. But on the other hand, when you see a quasar, chances are you're looking in the distant universe at an earlier time, at which time most of the galaxies were close together anyway. So whether that's the driving force for the activity is another issue. So at least we're as far as saying that they're the active galactic nuclei, and they're part of a whole, we were talking about this at dinner, a whole bunch of different kinds of active galactic nuclei, starting with very low levels like our own Milky Way, at the center of our Milky Way, up to the quasars. There are blazars, there are secret galaxies. There's a whole range of activity, and frankly, it's really not understood. I mean, obviously, you think that there would be a supermassive black hole in the center which is driving the activity, but just how all these things fit together is really not clear yet. There's a lot of work to be done.
Okay, you mentioned something about data miners.
Yes.
And this is certainly, I guess, this generation, I call it a generation yet, where as long as you have a computer connected to the internet, and all this information is freely available to most people, whether many people know what to do with it is another matter. But is this perhaps indicative of the time has come for data acquisition and making it popularly available, so that people anywhere in the world, at any institution, whether they have any money or not other than a computer, are able to shine their light on what they find and reveal it to everyone? Because certainly it's 50 years ago, this information would be open to a very, very few number of people.
Yeah, that is true. That's a good point, that along with all of this is a realization that it's too much for a few astronomers to handle. And it is true that I think the Hubble Deep Field was probably one of the first that just got the image and said, calibrated it and said, here, do something with it, and the whole community could access it. It may very well be the time for many more people to become involved in that exercise. It's just, you have to be really careful, because in astronomy it's very easy to overlook systematic errors. Generally you have to do a lot of corrections, and you have to do a lot of corrections before you sort of come to some conclusion. And more people who would like to do that's great. In fact, I think that will probably be necessary. Otherwise, I don't know how you're going to handle it, really. Get more computer programs, I guess.
Along with that question on quasars, do we understand yet what the gamma ray bursters are? What's the latest information as to what they might be, way out at the edge of the universe there?
Okay, you're straying a little bit out of my field of expertise, but the latest I have heard about the gamma ray bursters was that they were probably similar to supernovae, but hypernovae. I don't think that's universally accepted yet, but it seems to be the leaning that people are going. So it's like a very, very large, I'm just trying to think how to describe a hypernova, other than to just say it has more energy. Pardon? 30 masses, solar mass. Yeah, but you can get a supernova with 30 solar masses too. A hypernova requires more, maybe interactions with more dense objects like a pulsar or something like that, a neutron star of some kind. I better not stray too much because it's not really my field of expertise, but my understanding is that the leaning is in that direction, that it's these hypernovae that are going off and then interacting with the interstellar medium to produce their high energies. That's probably the best I can do at this point.
the problem of dark matter is that they're actually beginning to wonder if perhaps gravity needs to be tinkered with rather than the dark matter.
Yeah.
What effect is this likely to have on galactic studies? So presumably if the dark matter changes, everything else changes, and you're sort of back to square one.
Yeah, well, the strongest evidence for there being dark matter is simply that if you plot the rotation curves of galaxies, meaning that the way that stars go about the center, the rotation curves flatten off. And if you look at our own solar system, the rotation curves will fall off. In other words, you expect the velocity to go as 1 over the square root of r, where r is the distance to the center. You see that perfectly well in our own Milky Way. The velocity of Pluto is, follows that relation, so does the Earth and so on. What does that mean? That means that all the mass is inside, and the mass is in the sun, basically. Everything else is a little bit compared to the sun. Okay, so for galaxies, it should be the same thing. Like if you go far enough out, eventually all the mass is inside, and the rotation curve should fall off. And they don't. They're completely flat, which, if you work it out, means that the mass is going up with r. Every increment in r means an increment in mass. Okay. So there's no way that you're at the edge of the distribution. Now, that has always been taken to be this indication that there's no dark matter, that there is dark matter. Sorry. Now, the fact is that a great deal of effort is going into finding it without finding it yet. Okay, and it is, it started off being baryonic, and you can't find the baryonic mass, and you put more and more stringent limits. You look with the macho experiments, the oval, all this stuff, and you still don't find it. So you say, well, it's exotic matter. We need special detectors to find exotic matter. So then there's a group of people that says, well, hold on here. Maybe we're looking at this the wrong way. Maybe there just isn't any. Maybe we have to modify gravity. Now, gravity will not, what happens is if you work it out, it's a very small modification, and it's only a modification of a very low value. What you should do is put in small g is defined to be capital G m over r squared. Now put for m the mass of luminous Milky Way, 10 to the 11 solar masses. Put in r as 20 kiloparsecs or something. Switch it to the right units, and work it out. And small g is very, very small. It's a very tiny value. And if you change gravity in a small amount, such that you could not actually measure it on the Earth, you could produce these rotation curves. You don't have, the rotation curves are being reproduced now by doing this. The problem is, and the reason people don't like it, is because it's empirical. There's no theory that explains it. We have a good theory of gravity, good, whatever, you can take that to mean what you will, but how general relativity works in, how it reduces to Newtonian gravity, and that's a complete and fully formed theory. And when you fit these rotation curves with your modified gravity, you're just changing it to make it fit. The only constraint you have is that the amount that you change it must be the same for every galaxy. Because you can't arbitrarily change gravity for each galaxy, right? And it turns out that there's a parameter called A0, which figures into the calculation. And that parameter turns out so far to be pretty constant from galaxy to galaxy. Interesting. Time will tell which is right.
So, how seriously is the concept of variable gravity being taken? Is this just a parlor shop discussion, or? Well,
that's a very good. That's a really excellent question. And 5 years ago, nobody would have said boo, right? Nobody would have admitted it. There'd be a few people who might have said, well, maybe we'll play around, but they'd be the odd man out. But a couple years ago, I went to a conference, and a very well-respected astronomer got up and gave a talk about how he believed in this modified gravity theory called MOND. This one called MOND. And everybody just sort of, this person you wouldn't expect. And now, lately, there have been quite a few more papers out about it, basically showing how the rotation curves of galaxies can be explained in this model. A0 is similar from galaxy to galaxy. But you shouldn't underestimate the power of theory. When astrophysicists say theory, they mean something extremely well developed, extremely well tested, right? It's not just, you're theorizing. It's really something extremely well developed. And I think until this group, which seems to be growing, can put their models in that kind of context, they won't really be taken seriously. If they can do that, that's a different story.
So if I understand what you're saying, the work that's done so far is purely descriptive and empirical. Is there any theoretical background work being tried?
No, there must be. I'm not aware.
Sure. It strikes me as galactic morphology may be a good tool for trying to come up with that. Or am I full of it?
The rotation curve certainly.
Oh, wasn't there some evidence about maybe 10 years ago from your Uhura X-ray satellite finding extremely high temperatures of gas surrounding galactic?
Yes,
clusters?
yes,
Did you get it?
that's right. Yeah, many galaxies have gaseous halos. That is not to be confused with the dark halo. Those would be baryons. Those would be matter that we understand. In other words, matter that radiates and would be included in my estimates of all the luminous matter. That's included. Now, it is also true, though, that in some clusters of galaxies there are X-ray halos that maybe haven't been detected yet, or haven't. The X-ray astronomy is pretty young science still, and so it's possible that the consensus of baryons may increase due to those discoveries, but they're not going to get up to the numbers that you're really missing if you believe the gravity is right. It's not enough. And in fact, there's primordial nucleosynthesis. When you work out numbers according to the Big Bang and so on, you can calculate how many baryons, meaning radiating baryons, there could be. And it's way lower than the actual amount that you require for mass.
Hey, Dr. Curious to know your opinion. Has the Big Bang transformed from best fit model to fact?
I think in the astronomical community, it has always been fact for a long time. I mean, fact as much as people want to say. You always have to qualify these things. But there's always been strong evidence for the Big Bang. Now there is better evidence for cosmology. You can look at the fluctuations in the background and decide that cold dark matter works better than hot dark matter in forming galaxies, and you can make decisions like that. But most astronomers accepted the evidence for a Big Bang and haven't really wavered on that. It fits too well with all the evidence that you can see.
Well, to follow up, if I may, your slide was intriguing about our biases in a way that our view of the universe is limited by our biases.
It's true.
The way we look at it, the instruments we use, the wavelengths we play with.
Yes.
What I really find fascinating about astronomy is not so much the details of the cosmology, but also the human factors. Mm-hmm. And does anybody ever, in the professional community, ever touch on those human factors and how it forms and how those things form our opinions of what we see and how we interpret the data that we apply?
You've raised a very, very interesting point. Astronomers like to think that they're being objective, right? You try very hard to be objective, and even by saying that, you automatically completely discard any discussion of this opinion. And you know that there's always opinion being expressed in the literature, but it's based on some evidence or other, and the evidence is not always clear. It's just a fact. I think it's probably true that if there is a very influential person in the field that everyone respects and he has an opinion, that will carry the day for a while. But it won't carry the day forever, because you are using real instruments to look at a real sky and getting real data. And eventually, if that person is Shapley, for example, Shapley put the sun where it belongs. But he was wrong about the nebulae, and he argued strenuously about it. It will carry the day for a while, but I don't think it will carry the day ultimately.
And I have another question. You were talking about this up and down, where the galaxies created, like Venus, just became one whole thing out of the massive gas, or is this something like the little CD, you know, dominant galaxies going around cannibalizing on small things? What's the current belief on that?
Okay, there's two things that you brought up, really. One is that if two galaxies collide, you could take two spirals and have them collide, eventually fall together, and they can actually make an elliptical galaxy. And you can see that via n-body simulations on the computer, and you can see it in the sky if you sort of take snapshots of different examples. So it's thought that for making ellipticals, there may be at least two ways to make ellipticals. Okay. Now, for making disk galaxies, the current view, and this is probably going to change. This is something that everyone recognizes is the current view, and that we don't have open answers to this. But the current view is that small bits and pieces build hub. And it's not done in a simple fashion. It's very complex. In other words, you take some cold dark matter clumps and they come together and they virialize, meaning they become very random. But individual pockets of gas can do their own thing. And then when that is finished, more or less, then you get a settling down of a thin disk of gas within which star formation can occur. And then that starts to create a sort of disk system. But in the meantime, you continue to accrete these little satellites. And in fact, in our own Milky Way, you can see both a thin disk and a thick disk. And the thick disk is believed to be due to a specific encounter with a previous small galaxy at a specific time. They puffed up the disk and gave you two components. It's just not straightforward and simple. Now, the original idea was that you just get a big gas cloud and there's a monolithic collapse, right? But if you do that, what happens is star formation proceeds as the thing collapses, and then what you should see, I get this right, yeah, if there's more star formation towards the middle, you should see a gradient in metallicity, in how many heavy metals are present from the inside of the galaxy out, and you don't see that in reality. So that cannot be right, just because the prediction of that model doesn't match the observations. But the actual scenarios that I've given you in a hand-wavy fashion, I mean, that's about the best you can do right now. You just don't have the answers. Maybe we should not keep you too long, but
One more quick question.
Yeah.
We know that Andromeda Galaxy, our neighbor, is the only galaxy that we know that is moving toward us, the Milky Way. Now, maybe you can give us a prediction or a prophecy, but when Andromeda collides with us a few billion years from now, what is that going to do to our sky? And how is that going to change? This is interesting. How is that going to change the shape of the galaxy? Like you were talking about galaxy shapes.
Yes.
We are now regular shaped galaxies.
Yeah.
Does that mean that we will both become irregular galaxies?
I think so. So you can do this. This is actually not that hard for somebody to answer. Meaning you could put it on your computer and you can run the simulation. You can actually do that, and it has been done, I believe. So yes, you should get. I mean, M31 is a massive galaxy, right? It's as massive as we are. And when you see other binary galaxy systems that are of roughly equal mass, there's fairly significant distortions that result from that. The infall time scale on any galactic scale is about 10 to the 8 years. That's typical. That's like a rotation. That's how long it takes us to go around the center of our galaxy and come around, for example. So the sky should look different. But you'd have to run your simulation to answer your question properly. Maybe we can try and find who's done that so we can pull it out afterwards. We should stop answering your question. Right?
One more question.
People are asking all kinds of things.
I have a very general one. This gets back to the accessibility of all this data, and that astronomy seems to be rather a unique science in this, where a lot of this information has become freely available to anyone in the world. And it's kind of like the democratization of science, which is beginning in astronomy. And I was wondering if, over your short career, as it is now, if you've actually noticed any impact of this, or can you foresee an impact of this?
Well, I think I can foresee it more than I've seen it, because I think it hasn't happened for very long. the Hubble field is probably the best example I know where really for the first time the calibrated data were released. And it was marvelously successful. Lots of people got their hands on the data and did some very good things with it. The Canadian Galactic Plane Survey is now being publicly accessible. And most people are shifting now to that point of view. There might be a proprietary time period. Chandra, I think it's a year or something like that, I forget exactly, but typically it might be a year after the data are acquired, then they become public. And I think it is going to make a big difference. In fact, I think what it will do is it will make people like me stay home. Because, you know, let's look at it this way. I'm going to write an observing proposal, right? I'm going to spend a week writing an observing proposal and send it to an observatory. I'm going to wait 3 months until they get back to me and tell me whether I have time or not. If I get the time, then another 3 or 4 or 5 months down the road, I may have to travel to some observatory to get the data. And then I'm going to have to come back and calibrate it and do all that myself. And then I start to think about the analysis and doing something with it. Well, if somebody's already done that, you know, you can just sort of leap right ahead. So I think it is going to make a difference. And in my short career, I have seen similar shifts already. I remember my supervisor, who was Ernie Sequist in Toronto, lamenting the fact that in his day he would go out and take the wrench to the telescope, right, and fix the receiver. And nowadays he said, well, we just send you down to the VLA. Well, we're not going to the VLA anymore. I haven't been to the VLA for years now because I don't have to. I can just set up the observing run here, send it down via FTP, they run it, they send back the data. Okay, and that's in my short career. So I think we're going to see much more of that as time goes by. Whether you think that's good or not, I don't know. But when you're, you know, stressed for time and you really want to do as much science as you can, that seems to be the way to do it.
Dr. Irwin for one of the more challenging talks we've had in recent years in our annual banquet. I'd ask Deborah Tickner, our Vice President, who has something to present as a token of our appreciation.
On behalf of the RASC Ottawa Centre, we'd like to thank you very much for coming out here tonight. As you can tell with the questions after your talk, it's of great interest to everyone here and giving us a glimpse to the professional astronomical world. And just to let you know that you're also an inspiration and a role model to some of the young ladies who happen to be junior members of our society. So thank you again.